gradient vector of a function in several variables. We will define the gradient vector of the function fxyz in three variables as partial derivative of f with respect to x times vector I plus partial derivative of f with respect to y times unit vector j plus partial derivative of f with respect to z times unit vector k. So let's take an exercise. The partial derivative of, let's calculate the partial derivative of f given in this formula here. So the partial derivative of with respect to x will be y power 2 times z power 3 times I plus partial derivative with respect to y will be 2xy z power 3 times unit vector j. Then with respect to z is 3xy2 z power 2 k. So the final answer is a vector, but with variables x, y, z. So it's variable vector. Okay. So let's calculate this vector at the numbers 3, 2, minus 1. So let's give x3, y2, this is y2, z minus 1. So 2 power 2, 4 times minus 1, so minus 4i, x3, y2, so it will be 12 times minus 1, minus 12, j, x3, y2, z minus 1, so it will be plus 36, k. Okay. Now, how we can use this vector, the gradient, in the applications of function of several variables. So we can use it to find the tangent plane of the surface of a given function. So theorem. The tangent plane of the surface of the function fxyz equal a constant. So any function equal a constant is a surface in the space R3. So this the tangent plane at a given point m0, x0, y0, z0, if the tangent plane exists, and this means if the partial derivatives here at the point m0 exist, so everything here at m0, so the point m0 must be on the surface. So if I put here x0, y0, z0, so f at this point will be the constant, c. So the formula of the tangent plane is given like this. The partial derivative of f with respect to x times m0 at the point m0 times x minus x0 plus the partial derivative of f with respect to y at the point times y minus y0 plus the partial derivative of f with respect to z at the point times z minus z0 must be 0. This is the equation of the plane, tangent plane. Why this is correct? Because, in fact, the gradient at this point must be orthogonal to the tangent plane. So because of this, if I take the inner product of the gradient with the vector m0, m, where m is any point on the tangent plane, so this inner product will be 0 because they are orthogonal. And after that, we will take the formula. The x of this vector is partial derivative of f with respect to x. And the x of this vector is x minus x0, where x is the x of the point m. So we will product we will have this term plus etc. Okay, let's take exercise. Exercise, find the tangent plane of the surface of the function given here at the point. So let's verify at first that this point satisfies the equation. So let's verify. If I put here x1, y2, z minus 1. So let's put here x1, 1 times 2, so I will have 2 here. And here 2 times minus 2 power 2 times minus 1, so minus 4. Minus 1 power 2 times 1, so it's 1. So the final answer of this, okay, let's continue. 1 times 8, 2 power 3, 8 times minus 1. So minus 8 times minus, so minus 8, minus 7. So what is the answer? So here, it's minus 1 minus 7 plus 8 equals 0. This is correct. So the point M0 exists on the surface of the function S given by this formula. So now let's suppose that this is a function f. So let's write here f x, y, z equal this. So the tangent plane, the equation of the tangent plane will be the partial derivative of f with respect to x at m0. This is a real number times x minus x of m0, it's 1, plus partial derivative of f with respect to y at the point m0 times y minus 2 plus the partial derivative of f with respect to z at m0 times z minus 1 plus 1 equal 0. Let's calculate what is fx. It's 2xy, here 0, and here plus z power 2. And this term will be minus 3x2 y3 z3. So what is fx at m0? At the point 1, 2 minus 1. So let's write in red. So x1, y2, so it will be here 4, z minus 1, so 1 here. Then here x1, z minus 1, so it's minus 1 here, times minus plus, and 8 times the 3, so 24. 24 plus 5, 29. So the final answer here is 29. Okay. Let's calculate now the partial derivative of f with respect to y. So it's x power 2 plus 2yz. The derivative here of this term z2x is 0, then minus 3x3 y2 z3. So let's calculate fy at m0. So let's write in red here. I will give x1, y2, so here 1, y2 z minus 1, so minus 4. And here I will have 4 times 3, 12, plus 12, because minus by minus will be 0, will be 1 plus 1. So after that, let's continue here. 8 plus 1, so it's 9. So here it's 9, so the answer here is 9. Let's continue the calculation. The partial derivative of f with respect to z will be 2yz from here, the derivative of this part, the derivative of the first part is 0, and 2zx plus 2zx. Then here it's minus 3x3 y3 z2. Let's give x1 y2 z minus 1, so minus 4. Then here minus 2. And then here I will have x1 y2, so 8 times 3 minus 24. So it will be minus 30. So let's write here that the partial derivative with respect to z and 0 is equal to minus 30. Now, finally, what is the equation here? Let's write in red that this term here in the beginning, the answer is 29. And this term here is 9. And here minus 30. So the equation of the tangent plane, let's write the final answer here in red. So it's 29x plus 9y minus 30z. Here I have minus 29 minus 30. Okay. And here I have minus 18. So it will be everything in minus. So it will be 77 minus 77. This is the final answer, the equation of the tangent plane. Let's take this exercise. Find an equation of the tangent plane of z equal x power 2y at the point 1, 2, 4. Let's verify that this point satisfies this equation. So if I give x1, y2, x2, y1. Okay, so let's change only this here. So it's x. The question here is xy power 2 equals z. So let's solve this exercise. If I suppose that f x, y, z is xy power 2 minus z, so this is equal 0. So the equation of the tangent plane, tangent plane at the point m0, 1 to 4 as the partial derivative of f with respect to x at m0 times x minus 1 plus partial derivative of respect to y at y minus 2 plus partial derivative of f with respect to z at z minus 4 equals 0. Let's calculate fx here. So it will be y power 2. So fx at the point m0, it will be y is 2, so it will be 4. Let's calculate in another color. Fy is 2xy. So fy at m0 will be 2 times 1 times 2, so it's 4 also. Let's calculate finally fz at m0. So it's before m0, fz is minus 1, so it will be also minus 1. So the equation of the tangent plane will be 4 times x minus 1 plus 4 times y minus 2 minus 1 times z minus 4 equals 0. We can write it finally 4x plus 4y minus 4 minus 8. Minus 4 plus 4 is deleted, so we can delete this number here. This is plus 4, this is minus 4 after producting. So the final answer here, minus 8, is 0. Then we can divide by 4 also here. I forgot z. Okay. I forgot z. So minus z minus 8 equals. So this is the final answer of the tangent plane. Now, what is the definition of the critical point and singular point for a function in two variables? Let's at first remember the definition of the critical point of a function y equal fx in one variable, where let's suppose the point A in the domain of the function. So if the derivative of this point, the derivative of the function at this point is 0, then we will call this point critical. And if the derivative of the function at this point doesn't exist, so this means the derivative of the function at the point is infinity, maybe, and maybe it's not a number and not infinity. This is the meaning of doesn't exist. If the derivative doesn't exist, so the point A is called a singular point for the function f. Let's take these two exercises. The first one, fx equal x power 2 minus 6x. Let's calculate the derivative of the function f. It's 2x minus 6. So this exists for any real number x. So no singular points. No singular points, because the derivative always exists for any real number x in the domain, and the domain is R. Now, if I put the derivative is 0, then x equal 3. So this is a critical point. So we have only one critical point and no singular point for the function f here. Now, the second example, function jx equal root x. So here the domain is x greater or equal 0. So the number 0 is in the domain. So what is J0? J0 is root 0 equals 0. It exists. Now, what is J derivative x? It's 1 over 2 root x. So this is not 0. Okay? So no critical points. No critical points. But what is J derivative at 0? J derivative at 0 doesn't exist. So 0, x equals 0 is a singular point. Now, let's take the definition of the critical and singular point for a function z equal fxy in two variables. Let's suppose that we have a function fxy in two variables, and let's suppose that the point x0, y0 in the domain. So this means fx0, y0 exists. This is a real number. Okay. Now, if the gradient of the function f at x0, y0 equals 0, then by definition, the point x0, y0 is called a critical point for the function f. So what is the meaning of the gradient equals 0? This means the partial derivative of f with respect to x at x0, y0 must be 0, and the partial derivative of f with respect to y at x0, y0 also equals 0. Now, definition 2, that if the gradient of f at x0, y0 doesn't exist, So this point x0, y0 is called a singular point for the function. So this means the partial derivative of f with respect to x doesn't exist at this point, or the partial derivative of f with respect to y doesn't exist at x0, y0. Let's take some exercises. So here, find all critical and singular points of fxy equal x2 plus y2 minus 6x plus 10y minus 1. So let's calculate the gradient of the function f. Its partial derivative with respect to x, it's 2x minus 6 times I. So this is fx plus the partial derivative of f with respect to y, it's 2y plus 10 times j. So to find the singular point at first, we remark that this is this vector, the gradient f, exists for each xy in R, for any real numbers xy. So for this reason, no singular points, no singular points. Okay, now let's find the critical points, the critical points. Let's put f, this part 0 here, and also this one 0. So we will have 2x minus 6 equal 0 and 2y plus 10 equal 0. So we will have from here x equal 3, from here y equal minus 5. So we have one critical point. So the point x3, y minus 5 is critical point. What about if we have the solution of this equation, two solutions, and here one solution? What we will do in this case? Let's take an example. Let's change this exercise. For example, let's write here 3 in red here. Only this is the change for this exercise. So what is the change? For singular points, no change. Now for the critical, only the derivative here will change. So here the derivative will be derivative of x power 3, 3x power 2. Now here I have 3x power 2. So what is the solution of this equation? I have x power 2 equal 2. So I have two solutions. So here I will have two solutions. X equal minus root 2 or x equal root 2. So I will take this formula, this statement, x equal minus root 2 or x equal root 2, and the other statement. So what is the final answer will be in this case? So I will have minus root 2 minus 5 and root 2 minus 5. These are the critical points. Okay, let's take last exercise here. Find all critical and singular points for the function fxy equal root of 4 minus x power 2 minus y power 2. So here, let's calculate the gradient of the function f. What is the domain of the function f? domain of the function f, all of the points x, y in the plane r power 2 with the condition 4 minus x power 2 minus y power 2 greater or equal 0. So this condition also could be written as x power 2 plus y power 2 less or equal 4. So if we want to sketch the domain will be inside the circle of center 0, 0 and radius 2. And the points on the circle are included because we have here equal. So let's calculate the gradient of the function. So we have here, this is equal. The derivative of the term under the root 4 minus x2 minus y2, it's minus 2x over 2 times the root 4 minus x2 minus y2 times I plus minus 2y over 2 times 4 minus x2 minus y2 times j. Okay. If we put this equals 0 to find the critical points, we will have x0 and y0. So we have this point, let's write in red here, the point 0, 0 is critical point. Now, can we find any singular point? So if we remark that this term down could be 0. So this term down here could be 0. For example, if x2, y0, so this point 2, 0 exists in the domain of the function. But what is the gradient of f at this point 2, 0? Doesn't exist. So this point 2, 0 in the domain, it's one of the, it's in the domain, but there is no derivative, no gradient at this point. So this point is singular. So all of the points, so all singular points, all singular points are on the circle. X power 2 plus y power 2 equal 4. The circle of center 0, 0 and radius 2.